Applied Mathematics, and today I will do a presentation on a stochastic algorithms for intelligent telecom optimization. This presentation is supported by the Huawei company, and it is based on open source information from scientific books, papers, scientific overviews, and of course scientific competitions. So here you can see the content of the presentation. It is divided into three sections. The first section is related to telecom networks and related optimization problems. Here we will discuss what are the optimization problems in telecom optimization and what are the algorithms suitable for these problems. The second section is related to the trends in optimization algorithms. Here we will talk about the three in our sense, most important scientific optimization competitions, namely large-scale optimization competition, black box optimization competition, and of course combinatorial optimization competition. And the last section is more educational, more scientific, is related to the description of the main directions and main types of the optimization algorithms that are in some sense suitable for the problems discussed in the section 1. Search algorithms, genetic algorithms, so on, evolutionary strategies, differential evolution. So let us start with the first section, telecommunication networks and related optimization problems. In here we will consider three types or three classical optimization problems for telecommunication networks. The first one is related to planning and design of telecommunication networks. So you can imagine the first step in the telecom optimization is, of course, to plan, to build the telecommunication network. And this type of problem, of course, contains several sub-problems, such as network planning problem, multicast server assignment problem, multi-level network planning problem, multicast problem, hub location problem, network scheduling problem. On the left, on the slide, you can see a very simple picture that describes a case when we need to understand where to put a hub in the network problem. And of course, what we need to do usually is to minimize the total costs of the network by satisfying user demands and providing mean QoEs and respecting its capacity constraints of each link. On the right, you can see a mathematical problem statement. And in here, of course, we need to define a network design that minimizes the total costs while satisfying the user's demands. And actually what you can see is that this is a purely combinatorial NP-hard optimization problem, and sometimes even a linear combinatorial optimization problem. So we will not talk much about the details. You can check out this later, and you could use the links which are listed below. So the second class of optimization problems in telecom networks are called routing problems. So when the telecom network is already set up, what we need to do is we need to understand how the signal will move around the network. So given a set of connections, the problem is to set up a light path by routing and assigning a wavelength to each connection. And this type of problem is called the routing and wavelength assignment problem. The picture you can see on the left describes a setup network where we need to understand how the signal will move around the network. Classical related problems or sub-problems are multicast routing problem, routing and wavelength assignment problem, virtual routing problem, traffic rooming and routing problem, and so on. On the right, you can see a related classical mathematical optimization problem, which again is an NP-hard combinatorial optimization problem. And here we need to define a route that minimizes the maximum transmission distance between the nodes in the routing path and maximize the hop count. Of course, you can understand that it's not only an NP-hard combinatorial optimization problem, it is surely a high-dimensional combinatorial optimization problem. But about this we will talk a little bit later. The last but not the least type of the optimization problem is called the channel allocation and configuration for telecommunication networks. Actually, sometimes this problem is divided by two, but we have decided to put it into the one problem. So what we need to do? Typically we need to allocate the limited frequency spectrum to secular mobile networks under the interference problem, which is a phenomenon that represents the superposition of two or more electromagnetic waves of the same point. So you can imagine that we have a user of a mobile network, and we need to understand how to allocate the frequency, for him of a certain base station or of several base stations. And the problem could be is that the frequencies of different base stations could interact with each other. That's called the interference problem. And another subproblem is called a parameter optimization, where we need to understand how to control our base stations in order to maximize the throughput or the signal for all of the users. The classical channel allocation configuration problems are listed on the left, which are the frequency allocation and interference problem, coverage problem, where we need to understand what kind of parameters of the base stations we need to use in order to cover all of our users, yes, and resource allocation problem. On the right, what you can see is actually a description of this type of problems. And simply, we can say that these problems are or can be considered as a black box optimization problem. Not only black box, but a high-dimensional black box optimization problem. Why? The problem is that the mathematical equations of a wave or of a propagation is so complex that it is much easier to consider this problem as a black box problem, where we don't know how the objective function is calculated, and we do not want to know anything about the gradient of this function, or we don't want to take a derivative because it's so complex. We just want to consider this problem as a black box. What does it mean, and why we want to use a black box? So on the right, you can see a very, very classical test function for nonlinear high-dimension optimization or even black box optimization, which is called a Rastrigan function. Yeah, and we can consider a problem to be black box when our objective function is nonlinear, non-smooth, non-convex, and also we can consider it when it is hard to calculate the gradient of the objective function, or even it's impossible. On the right, you can see several links. So now we can understand that that the channel allocation configuration problem for telecom networks is actually, or can be considered as a high-dimensional black box optimization problem. Now let's consider a world-known and classical example from France, when the researchers applied evolutionary algorithms in order to optimize the antenna placement and radio coverage of an area. So this project and the corresponding data comes from the open source, open source information, and the provider of the data is a France Telecom Research and Development Center, and this data is related to the ARNO project for the developing of the optimization methods and associated software for secular network engineering. So, as I said before, the idea was to optimize the radio coverage of an area and antenna placement all together. So this is kind of a combination of a planning task and optimization, tuning of the network task. So it was studied, and the real data was taken into account. Researchers managed to reduce the number of antennas on a site up to 50% from some manual configuration or some engineering configuration. So that's a huge reduce of a cost of a users. So this supports the idea of using mathematical optimization for this kind of problems. So on the right, you can see mathematical problem statement for it. So what they actually wanted to do is they wanted to use a multi-objective optimization in this problem, and each objective represents a site costs, so the number of used sites or antennas, interference level, and self-shave factor. But usually when we consider a multi-objective optimization problem, it is easier for us, for people who work with algorithms, to consider a single objective and use some linear combination of these three objective functions. That's what you can actually see where we need to minimize this linear combination of these three objective functions. And the control parameters of antennas were the antenna placement, of course, because we want to solve the problem of planning, power, tilt, and azimuth. And constraints were the traffic constraints, so we had to fulfill the demands for the traffic, and the coverage constraints, where we have to cover a given number of users. So on the right, you can see several pictures which are related to what I have just said. And so the result was that they managed to reduce the number of antennas up to 50%. That's very, very excellent. What you can see now on the slide is actually a simplified technology map for the algorithms that can be used. The first two columns, of course, should be very simple and known by you, which they represent very simple and very fundamental academic approaches for optimization, such as dynamic programming, branching bound, and so on. But on the right, you can see modern techniques for this kind of optimization problem, which is random search algorithms. We'll talk about this later. They're suitable for most of the combinatorial optimization problem, but anyway, they are a little bit outdated, but sometimes they're used as a component solvers. Swarm intelligence algorithm, more modern, also semi-powerful, used for different types of optimization problems, combinatorial, continuous optimization. Genetic algorithms primarily used for combinatorial optimization problems. A little bit old-fashioned, but still are very powerful for combinatorial. Yeah, still some of them are state-of-art. Yeah, differential evolution algorithms, evolutionary strategy algorithms, and estimation distribution algorithms are more modern. I would say they compete currently. Differential evolution strategies are the state of art now for the scientific optimization. Estimation distribution algorithms are even more complicated, more modern. And they also actually are now widely used for machine learning optimization, but currently they are a little bit complex for the calculations, and therefore for high-dimensional problem they are not very suitable. So let's discuss what are the trends in optimization algorithms. Yeah, but before we will go into that, I want to say that as a mathematicians, we should not only consider what are current ways for solving telecom optimization problem when we want to do that. No, we should consider a mathematical abstraction. We need to know, we need to understand what kind of optimization problem this is. For example, we have considered three types of optimization problems, and there all the time I was stressing that that's a high-dimensional, combinatorial, or sometimes continuous black box and so on optimization problem. And this is where we need to start thinking about what are the best mathematical algorithms in this direction. And of course, one of the ways to do this is to consider world competitions. Yeah. So let's start with the results of the large-scale optimization competition. which is organized during the III Congress on Evolutionary Computation. And during this competition, the organizers are using 15 benchmark functions with more than 1,000 dimensions. And these benchmark functions all have different types, all different shapes, can be single or multi-objective, constrained, unconstrained, and so on. And the organizer are measuring each algorithm of how they perform for each of these functions. Then they use some classical sporty techniques to measure who is the best. And what you can see below is the list, just a simple list of winners in this competition. In 2019 is CC RDG3, in 2018 Shade ILS, from 2013 to 2018 MOS, which is actually a combination of several algorithms. On the right, you can see of how these algorithms are actually compared. So you can see a picture with the results from 2019 and top 4 algorithms and of how they perform for each type of the optimization function. Yeah. Let's look deeply into these 3 top algorithms. Yeah. So the first algorithm is actually a combination of cooperative convolution, modified recursive differential grouping, and covariance matrix adaptation evolutionary strategies. Yeah. So this algorithm is actually related somehow to the evolutionary strategies. The second algorithm, Shade ILS, is a hybrid algorithm that combines a dynamic local search. You can see dynamic local search, so that's a random search algorithm, and differential evolution. We will not talk about much details. Yeah, and the last algorithm actually uses a multiple offspring sampling to combine the results from differential evolution and IPOP semi-AS, which is a combination of differential evolutionary strategies. All very interesting. What is important? What's important here? Important thing is that, of course, we cannot say that one of these algorithms is the best in the world. Yeah, we cannot say that, but we can say that they are potentially interesting to look for, to start your research, because they are kind of equally good perform in different type of optimization problem. Second competition that we can consider is called a black box optimization competition. And this black box, this competition is held during the Genetic and Evolutionary Computation Conference, also very well known. And here they consider different fully black box optimization problems where the participants do not know anything about the objective function. The only thing they can do is to send a solution and then to receive the value of the fitness. That's it. And on the right, you can see the list of the winners. Sometimes participants can hide the description of their algorithm. Yeah, so that's even black box for us when we study the results. But what you can see is that the top one is ACAC semi-AS, yeah, so that's also evolutionary strategy. And number 4 is actually related to L-shade, so on. So that's kind of differential evolution algorithm. Of course, we cannot say that they are the best in the world, but it is important to look for it. And the last competition that we want to consider is related to the combinatorial black box optimization competition. And in here we use different types of black box functions, but most importantly for us is that all of them are. Last part of the presentation is related to the description of various directions of stochastic algorithm, such as random search algorithms, genetic algorithms, swarm intelligence, differential evolution, evolutionary strategies, and estimation distribution algorithms. They can be used as a component solver. We can combine this algorithm with several different algorithms and maybe combine them all together. Yeah, And but the problem is that these algorithms do not directly provide us the global optimal solution always. Yeah, because these algorithms are a stochastic algorithm. So we need always to keep in mind, and we need to have some kind of trade-off on the performance or efficiency of this algorithm and computational resources that we use for them. Yeah, we need to understand how to tune hyperparameters for all of them, and using it, we can try to find as good solution as possible. Unfortunately, we do not have enough time for me to present you all the various type of these algorithms, and the last slides of the presentation I will keep for myself. But if you're interested, you can write to me, you can contact me, and I will try to send you this presentation if that would be possible. So thank you very much, and see you.